Hello everyone, this is Lab 5 following Slinky for Physics 2211. So the purpose of this lab was to predict the motion of a slinky under the effects of gravity and drag. Our experimental model was made using Tracker, and our computational model was made using GlowScript, and then some physics principles involved in this lab were Newton's second law, weight force, and the drag force. The result was that the computational model closely resembled the experimental model, successfully replicating the motion of the falling slinky. So before we go into the data, let's define some of these principles, starting with Newton's second law. This law states that the net force acting on an object is equal to its change in momentum divided by a certain time period. Using this law, we can derive an equation known as the velocity update formula shown here, and then we can use that equation to derive the position update formula, which is shown here. These equations can be used to predict the motion and position of a given object after a certain time period. Then we have the weight force, which is the gravitational force that the Earth exerts on an object near the surface of the Earth, and this is one of the forces applied onto the slinky. The second one is the drag force, which is the force from air resistance onto an object, which always opposes the motion of the object, and this is another force that's applied onto the slinky. And so for the procedure for this lab, first we're going to define the system as the slinky, then we're going to use the given video to analyze the bottom of the slinky's motion using Tracker. Then we're going to compile the data of the slinky's relative y location over time into a spreadsheet. Then we're going to code a computational model of the slinky's motion using the given measurements. And then we're going to compare the position data from the Tracker video and the computational model for each time step. So here's the observed model. As you can see here, I imported the video into Tracker and then created a relative coordinate plane with the origin being at the bottom end of the slinky, and then used the height of the guy on the left as a calibration stick. We don't know the height of the guy, so I'm using an average male height of 1.75 meters. Then for each frame in the video, I recorded the slinky's relative location, which resulted in a graph right here of the spring's y displacement over time and the data points for each frame. And now here's the computational model. Going into it, I also had to look up the average mass of a slinky, since that wasn't given to us either, and I got 0.2 kilograms. First, we define the initial conditions of the spring as shown in the bottom left, labeling the mass, initial position and velocity, which are both 0, and some other constants like gravity. Then I split the slinky's movement into two phases, with the while loop iterating through each phase. The first is the entire duration where the bottom of the slinky doesn't move, and then the second phase is where it begins to fall down. We use our physics principles and update formulas to simulate the movement of the slinky. I kept running it and kept doing some changes to the code until I got a coefficient B for the air resistance that resulted in a graph that was similar to our real world scenario. So then we bring the data from the computational model and the experimental model onto a chart which looks like this. As you can see, the two models are really similar in shape and allows us to assume that the computational model did a pretty good job at simulating real-world physics. And now for some possible sources of error, the first one being rounding errors. Data values from Tracker and GlowScript were rounded, altering the results from their true values. The second was the use of the trial and error method to get our coefficient B. It didn't result in an exact or perfect value, it merely just gave us a value that was good enough. And the next one was human error. Imprecise tracking of the mass altered results from the true values. So now for a further question. Why does the bottom of the slinky stay still? When the slinky is suspended in the air, it keeps extending due to gravity until the extension length becomes great enough to cause the spring force to be equal in magnitude to the force of gravity. The spring force is directed anti-parallel to the force of gravity, meaning that the bottom of the slinky is in static equilibrium. That was the end of this lab. Thank you for your attention.